Hello and welcome back to the second video in topic 2 that I'm going to make, and this lesson we're focusing on acceleration and velocity time graphs. So last lesson we looked at velocity, how we calculate it, and then basically be able to calculate velocity from a distant time graph. Okay, I'm just going to go quickly back over this. So this was our distance time graph, and the key difference is when you look at these graphs is this has got meters on the side, but they both have seconds, and we're going to go on to see velocity time graphs, how they're slightly different. Okay, first of all, we need to be able to calculate acceleration though. So, how do we do that? Alright, so we use this equation here. Acceleration is equal to velocity divided by time taken. Now, velocity, I forgot to mention, the other one is measured in meters per second. Acceleration is measured in meters per second squared. Okay, so if you can see that from there. Alright, and therefore we're going to draw and make a little triangle up here. This time I've got v minus u. Now v minus u, you might be thinking, what is v, what is u? Well, v is our final speed and u is our initial speed. Okay, so let me give you an example. So here's an example of a Bugatti Veyron. So it can do 0 to 1,609 meters per second in 25.9 seconds. Okay, so what's its acceleration? Alright, so basically what we're saying here is its final speed is this and its starting speed is this. Now this is going to give us a positive outcome, and the acceleration here is 62.14 meters per second squared. However, if we were decelerating, the numbers could be the other way around. So this might be our 0 might be our final speed, and this number here, this 1,609 meters per second, that could be our starting speed. That would actually give us a negative number, which is fine. So the negative basically represents that an item is slowing down, and if it's positive, then it means it's speeding up. Alright, okay, so from acceleration, from calculating acceleration, what we can do is we're going to look at velocity time graphs. Now, as you can see now on this side, here, instead of being meters, it's meters per second, and you can't see this because I'm currently hiding it. So let me just press this. Now I should be hiding. You should see down here it says time. Okay, so coming back again, we've got these different points occurring on the graph. Now at point A, what's happening in the first 10 seconds, we've traveled to a speed of 30 meters per second. Alright, then after between 10 and 50, okay, we've increased our speed again from 30 to 50, but this time you can see that there's a curve. Now the curve basically means that we've got a changing acceleration, whereas a straight line means a constant acceleration. Now at this point here, between 50 seconds and 70 seconds, we've got a constant speed, okay? So we haven't stopped, now we're moving at 50 meters per second. Alright, and then from 50 meters per second, we decelerate to 90 meters per second. So if I hide this, you should be able to see it there. Okay, what's crucial, though, is that we can calculate the acceleration from these graphs. Alright, and I'll base this on A and B, because they're the easiest. So the steeper the line, the faster the acceleration. Okay, remember that as well. Now, the first part, we accelerate to 30 meters per second in 10 seconds. And if we go back to our equation for acceleration, then what we have is the change in velocity divided by the time. Now, the change is 30, and it's measured up here. And the time is 10. So if we were to do this, we do 30 divided by 10. That's going to give us an acceleration of 33 meters per second squared. Okay, nearly got it wrong there. Alright, and then let's look at B. Okay. So our final speed is 0, our starting speed is 50, so we do 0 minus 50 divided by the time it takes to stop, which is 20 seconds because we're going between 70 and 90. Alright, so 0 minus 50 gives us minus 50 divided by 20, so to work this out in my head, so we're going to decelerate there at 2.5 meters per second squared. Okay. So this deceleration is actually slower than this acceleration here. Alright.